Hi, this is Leach with Simpson Math, and in this video, we'll be talking about conic sections. I'll be introducing conic sections to you. We'll be looking at their graphs and finding the equations of them while in the general form and how to be able to distinguish between them. So just a first note is that this is not a derivation. I'm just introducing these conic sections to you, so this is just an introduction. All right, so suppose that we had two quadratics with different variables, so an x and a y. So we have ax plus b squared, which that's a binomial squared, which is a quadratic, and then cy plus d squared. And those a, b, c's, and d's are just some real numbers, don't really care what they are. All right, so now I'm going to take these two different quadratics, these two quadratic expressions, and let's add them together. So in order for me to add them together, I'm going to need to FOIL them. So that's them FOILed. That's just a binomial squared. So we end up with this. So we just FOIL those binomials. And then I'm just going to rearrange the terms. And I like to have the squares first. So my x squared term, then my y squared, then my x, then the y, then my constant. So notice b squared and d squared do not have any variables attached to them. So it's like sort of kind of that progression, constant, linear, the quadratics, linears, constant. All right, I've just lightened the coefficients here because I don't really care about these lowercase a, b, c's, and d's. It's just the fact that there are coefficients of some sort. Those numbers might be something, and then I'm just going to actually replace all those a, b, c's, and d's with capital a's, b's, c's, and d's. So we have a capital ax squared, and then a capital C times y squared, capital dx, capital E, y, and then capital F. You might be asking yourself, what happened to b? Well, we're typically not going to see it or deal with it, but technically in the general form of the quadratic, which is what this is, there is this bxy term. We'll see what it does to the graphs, but ultimately we're not going to be messing with it for right now. So just don't really worry so much about that. But so we have our ax squared plus cy squared plus dx plus ey, then lastly that plus f. All right, I'm going to move over to Desmos, a online graphing calculator, and I'm going to type this in and then set this equal to 0. What this is going to allow us to do is going to allow us to graph this equation. Notice that I did not call this a function. This is not a function. These are just a set of equations. But one note is I'm going to actually move this f over and call it f on the other side of the equal sign. Technically, I guess you could do a negative f, but I'm going to do a positive f on the other side of the equal sign. So I'll see you over in Desmos. All right, here we are in Desmos, and I'm going to go ahead and type in that equation. So ax squared plus bxy plus cy squared plus dx plus capital EY, and then I'm going to go ahead and say equal to f. It just makes a little bit more sense in our equations for it to be equal to those, to this f, just for the numbers. All right, so it says add slider, and I'm going to tap the all button. By the way, this is just a teaching thing. This is not a thing you have to do. Feel free to follow along and play with it if you want to, but this is just a teaching introduction thing. So this is not a skill that you're going to have to be able to recreate. All right, so here we have our first conic, and it just looks like this sideways oval. And instead of calling this an oval, I'm going to actually refer to this as an ellipse, which is its proper name. So this is an ellipse. This is the first of our three conics. Let me actually first explore this b and then set it to 0. So as I move around this b a little bit, notice I'm making it bigger. It gets to be just a skinnier oval, and now it breaks apart seemingly and becomes this almost pinwheel looking thing. All right, so let me head back in the other direction, closer to 0. As I get closer to 0, it becomes more circular, and then it starts warping in the other direction. Then we get another hyperbola type thing. So actually, I used a word you don't know yet, but this weird looking pinwheel thing. What this B does is it controls sort of kind of basically the slant of these conic sections, and we're going to be dealing only with are conic sections that shifting horizontally and vertically, and then those that are in the directions horizontally and vertically. So we're not going to be needing to deal with B. So I'm just going to set B to be 0 and leave it there. All right. So let's play around and see what happens here. So I'm going to actually mess with D, E, and F first. So I'm going to adjust D. And notice as I make D bigger and smaller, D is the coefficient of the X. So this is dx. So notice as I make it bigger one way or the other. It also, this circle, this is an actual circle that we're seeing instead of an ellipse. This is a circle. The circle is getting bigger and smaller and moving horizontally, which should make sense because it's the X. I'm going to do the same thing with the E and adjust it here. So it's getting bigger and smaller as it's moving vertically along the y-axis, and that makes sense, right? And I'll set it down. And then this F, if I do F, notice here what it's controlling is in this case, it's controlling the radius. If I go negative in this case, I actually don't have a graph. I could zoom out and search around. There is no graph right here. If I was to set this to be exactly equal to 0, you're actually not 0 in this case. If I was to adjust some things, it reaches a point between where you can see it and then you don't, but it actually would be a point. So there's also a way to make this be a point, just a single point, which isn't something we're going to be concerning ourselves with too much, but there's a technical moment that goes from circle to point and then nothing. All right, I'm going to move D and E to 0. And then I want you to observe something about F here. So obviously, like I said, right here, when it hits 0, there actually is a point at 0. So this equation currently is 1x squared plus y squared equals 0. And so what are the x, y values that would make that be true? Well, 0 and 0. 0 for the x, 0 for the y. So the ordered pair is 0, 0. So that actually is a point at 0, 0, but you can't see it right now because it's just a mathematical point. So notice when I move, what's my radius? What's the F when I get a radius of 1? So right about here, we get a radius of 1. Notice F is 1. Okay, so let's move up to get a radius of 2. Moving on up. Oh, past it just a little bit. There we go. Now I have a radius of 2. And what's my F? Okay, it's 4. And let's move on up to my radius of 3. And when I get a radius of 3, notice that my F here is 9. So you should notice that there is a squared relationship here between the radius and this F value, the value that's on the other side of the equal sign. Right? And that is no accident. I'm going to put this F back down to like, I don't know, 3 or something. Okay, so we should be able to understand here a little bit about what's happening in terms of it moving left and right. But all you've seen me just move around in terms of x's and y's and the constant is this are those the linear and the constant term. So we have a circle. I'm going to be adjusting the a and the c. So let me adjust the a first. This is the coefficient of the x squared. So if I make it be bigger, notice what's happening here. It's becoming that ellipse, that oval, but it's becoming what we will call a vertical ellipse. It is tall and skinny. All right, and if I go back in the other direction, there reaches a moment that it becomes a circle again when it's 1, and then it gets to be a wider oval, and then it does disappear, and then it gets this weird shape. Well, let's worry about that weird shape in a second, but so we can have a wide oval to a tall, skinny oval, and then if I move the C, notice the C is affecting this in the horizontal direction, all right? So there's a few things going on here. Also, again, if I do the C negative, I get that weird pinroll looking shape. So as long as I'm keeping within this particular function, as long as I'm keeping A and C positive, I'm getting these ovals. Let me put it into this an oval that's like this. Let's adjust the D a little bit. All right, so if I adjust this D around, this is affecting that shape. Sorry, not the shape really, just the size and location like we saw earlier. Same thing with the E, it's affecting that size and location. And then F, it's kind of like acting like a radius, and it works into a point when it goes negative and we don't see it anymore. That makes sense as it follows along with that circle path. All right, so here I have a tall and skinny oval. I could basically switch them and get a very similar looking short and fat oval that's the same way as the other, the same as we saw a second ago. Notice, so again, A and C are affecting horizontal and vertical things. And when equals each other. So here A is 3 and C is 3. So with this, notice again we have a circle. Here though, my radius is not perfect. So here I have F, which is 4, and that radius isn't perfect. That's because my A and C's aren't just 1. All right. So we have ellipse, and I'm going to define the circle not as its own special conic section. I define circle as just a special case of the ellipse. It's the moment when A and C are the same. So when A and C are the same, then we have a circle. And here we have an ellipse as long as both A and C are positive, or I mean, I have to just switch the sign of the F. Both A and C are negative. Both A and C are negative, and we have, like I moved F to be negative in this case. Function values that make it work. Then they can also be an ellipse and be negative. In a minute, I'll define this as A and C have to have a product that is greater than 0 for us to have an ellipse. All right, so there's the ellipse. Now, what about this weird shape? Let me put F back to being positive. So what about this weird shape? So notice this happens when A is negative and C is positive, or the other way around, A is positive and C is negative. Now, they don't get the same thing when one's positive or the other's negative. We do get sort of kind of different or competing results in terms of the direction they open. This particular shape is something that we call a hyperbola. Not a parabola, a hyperbola, spelled with an H. Hyperbola. All right, this hyperbola shape is actually a set of X-shaped asymptotes. So there's actually two intersecting diagonal asymptotes, and the hyperbola fits in between the intersection of those. In some later lectures, we'll talk about graphing those, and we'll see that. So these parabolas have these two sort of kind of wide, rounded, V-shaped graphs, and they could be horizontal like this, or it could be vertical like that. All right, but the notable thing is that A is positive, C is negative, or vice versa. A is negative and C is positive. All right, now there's one more conic section, and that is the parabola. If you were to think about our parabola that we know, it's y equals x squared. That's its parent function. So if I was to toggle these sliders to get y equals x squared, well, that means that the c would be 0. So the c would be 0. And then if it was just y equals x squared, d is 0, e is 0. Oh, not e is 0. E is actually 1, because that's y is 1. And then my f would be 0. So that is actually, a would be 1. And this, that's why it's upside down. If this was y equals 0, then I would need to move the y to the other side, so I can make this be a negative 1 for the y. Now, it is not crucial that you be able to do that, but so this would actually be our parent function, just y equals x squared. So a parabola is a special conic section. Now, I'm going to point out here, so notable, a is 1, so the x squared coefficient is 1, or just exists. So we have parabolas here, but the coefficient in front of the y squared is 0. So I can adjust the d, I can adjust the e, I can adjust the f, not the b. We're not messing with the b. That really warps things out. So leave that b alone. I don't know why I even touched it. It's hard getting that to be 0 again. There you go. Just force it. So all these, I can just basically all of them to get all these different versions of a parabola. It just moves things around. But the moment c is no longer 0, here we have a hyperbola, there we have an ellipse. Only just the moment when c is 0 will we have a parabola. I can actually let this play, and you'll see, so there's an ellipse, it's moving back down to parabola, hyperbola, 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 parabola, ellipse. And there reaches a point when it gets to 1.2, there's a circle, then it's back to an ellipse, then it's back to a parabola, so it moves on through there. So let me move a up a bit, I'll do that again. So here we have ellipse. Once it gets to 3.7, it's a circle, back to being an ellipse. Now it's once it gets to 0, it's a parabola. and then moves on to a hyperbola. All right, so if I set C to be, let's have C be something, let me set A to be 0. All right, so notice here, this is also a parabola, but what's weird about this parabola is that it is a horizontal parabola. It opens to the left or to the right. You have yet to see this. This is why I made a note earlier that these are not functions. Circles, ellipses, hyperbolas, none of those are functions. We only have one of our conic sections that is a parabola. I'm sorry, that is a function, and that's when it's a vertical opening parabola. Here, this horizontal parabola, or if it was to be turned sideways, which is possible, turned diagonal, that's if we start using the B, then it is a sideways parabola. And we can have these other values that measure and that affect and change around this horizontal parabola. But again, the moment that this A is no longer 0, it goes to being an ellipse, or it could be a circle, or it could be a hyperbola. It has to be exactly equal to 0 for us to have that. Here, I could barely have this be an A, that it's not quite 0, but once you see that this is going to, there it is, there's the other part. This is not a hyperbola, so it's not a parabola. Flip this over to negative 0.1, and just barely there, it switches from being a parabola there, there's an ellipse, there's a hyperbola, there's an oval or an ellipse. So notice it's very, very, very picky. It has to be exactly at 0. All right, so let's summarize these values. I'm going to go back to my notes, and so we can summarize these. All right, so the general form of a conic. So again, we have the same formula. I'm not worrying about the BXY, but just a technical note for this to be a conic, A, B, and C all can't be 0. So if A and B were 0, that'd be fine. This would just be a parabola. And then technically, even you can have this, and that would still be a conic that's been rotated in some fashion. But again, we're not messing with the B. All right, so if we're given a non-degenerate conic, this is a vocab term that is not, you don't really need to worry yourself too much about it, but the non-degenerate conics, those are just the ones I just taught you. So ellipse or a circle, it's a special case of it, the parabolas and the hyperbolas. So all those are the non-degenerate conics. A degenerate conic would be one that's a line, intersecting lines, or point. So technically they can fit into this form. They can even come from a cone, which you'll see in the next video, but they aren't one of our conics of significance. They're quite trivial. And then also technically it is possible in this form with the right combination of coefficients to have actually parallel lines or even no graph. We saw that with Desmos. It's possible to have no graph by just especially that F, you move it to a value where you don't get any real roots that work. So basically I'm saying is, if I'm saying, hey, here's a conic, and it's one of our 3 conics, it is an ellipse, a parabola, or a hyperbola, well then, if the product of A and C together is a positive number, is bigger than 0, that means they have the same sign. They're either both negative or both positive, it's an ellipse. Then if we have a special case, so if A and C also are not just the same sign, but the same value, the same exact number, then we'll have a circle. So you can think of an ellipse. We have an ellipse that's not a circle when A and C don't equal each other, but their product is bigger than 0. All right, then we have a hyperbola when their product of A and C is less than 0, because they have opposite signs, or you can think of that negative in the form of a subtraction. And then lastly, we have a parabola when either A is 0 and C is not, or A is not 0, but C is. So basically, it's only when we only have one square term where we see the parabola. All right. So this is our general form of a conic. We have this new set of equations. These are not functions. And now you might be asking yourself, okay, he's calling these things conics. Why? Why is it called a conic or a conic section? Well, in the next video, I'm going to want you to watch and then play along with me. There is an online virtual manipulative. With that online virtual manipulative, you're going to then play around with the different sliders. You're going to be adjusting this plane as it intersects this double cone. There's these 2 cones that are stacked on top of each other, and they create these certain types of shapes that come from our these conics. So play around in that video, and then there's a third video that you're going to watch that's going to then come back and talk more about the formal definitions of these conics. So go play around to see how we can cut a cone to make these shapes to get these graphs, and then the third video is when we're going to explore the definitions. All right, so check those out, and I'll see you in the next video.